The first thing I need to do to make a figure after I have the graph made is the caption. And I can start by saying figure or fig1 and then a title. And here I've started a title for you, the incubation time of prairie lizard eggs from Arkansas and Missouri. One thing I should probably do to make this better is to put the name of the scientific name of the species here. I think that's right. And I need to italicize that. Remember, whenever you write scientific names, the genus is capitalized and the specific epithet, the second part, is lowercase, okay? And it must be italicized. If you write it by hand, you underline it. Okay, the second sentence, the first sentence is a title. Notice we never put titles on the top of the graph. The second sentence of the caption is a title. And so we want to say a couple things here. First of all, how different is Arkansas from Missouri? And so let's just start by saying Arkansas lizards had a longer incubation period than Missouri lizards. All right, now we need to put a number to that. How different are they? We could say how many times different they were, but probably with a number like this, we should do percent difference, because this one's 53, this one's like 55. They're not going to be that many times different. So let's calculate that out. So looking at the raw numbers here, and let me open up my calculator app here. Okay, so the way to find the difference between the two numbers is I take the greater number. If I want to see how much more one is than the other, I take the greater number, 55.8, minus the lesser number, 53.4, divided by the lesser number. Okay, and now I multiply that by 100 to turn it into a percent. Okay, so what I did is I took Arkansas's value here, 55.8, minus Missouri's, divided by Missouri's times 100, and I get 4.5 essentially. So I'm going to go in here, I'm just going to round it to 4.5 for my caption. Arkansas lizards had a 4.5% longer or greater incubation period than Missouri lizards. Now at the end of this sentence, before the period, I'm going to open a parenthesis and I'm going to say n equals 10. N stands for sample size. That's how many lizards there were for each average. And so both Arkansas and Missouri incubation times had 10 numbers. Okay, so N equals 10. And then I'm going to type in mean, the word mean. That tells the reader that these blue columns are averages or means. And I'm going to go to insert symbol. And I'm going to find the one that looks like a plus minus sign, one on top of the other. Mean plus and minus SE. That tells the reader that these error bars here and here are +1 standard error from the average and -1 standard error from the average. And one more comma, P equals. And now we're going to put, after that equal sign, we're going to put the outcome of our t-test. So we haven't done the t-test yet, so we go back to Excel and we put an equal sign and we type the word t-test. And then we open a parenthesis. And what happens is it tells you what to do then once you open that parenthesis. It says array 1, array 2, tails, and type. So for array 1, that's just the raw numbers for Arkansas. We don't include the average. We just include the raw numbers. Okay? And then we put a comma. And then it says array 2. That becomes highlighted. That means highlight the Missouri numbers. Comma. Then it says one tail or two tail. Well, when we only predict a difference, we don't predict direction, we do a two-tail test. If I would have said Arkansas will have a longer incubation time, I would do a one-tail test, but I predicted a difference. So we put a number 2 right there for a two-tail test, and then another comma. And then lastly, it says, is this a paired test? A two-sample with equal variance or a two-sample with unequal variance. This is not a paired test. A paired test would be like if you took the same person, the same group of people, and you checked their heart rate before exercise and after. That would be that would require a paired test to see if they were different. we're going to go ahead and assume number 3. Throughout the semester, number 3 is usually the one you'll use for most of your experiments. Okay, so number 3. 2 samples, unequal variance assumed. We're just going to assume the variance is unequal. Don't worry about it. Just put number 3. Okay. You might do a paired test when you design your own experiment in a different exercise, but we don't have to worry about that today. Then we close the parenthesis and we hit enter, and we get a number. All right. So for all of our experiments in Bio 2, our alpha value, our alpha number is 0.05. You don't have to type it. I just typed it so you could see it. What that means is that when you run a t-test, you get this number here, and this number is a p-value. Okay, this is a p-value. Okay, now an alpha value is a number that you pick, and you say, okay, any number lower than this when I do when I get a p-value is significant, shows a significant difference. And any number equal to or higher than this is not a significant difference. Well, our p-value is 4.29 times 10 to the negative 5th. So our p-value is way less than our alpha value. Therefore, we can say that these two numbers are significantly different. We're not allowed to use the word significant in science unless we've done a test like this. And in this case, we have 2 different samples. When you have 2 samples like this, you can do a t-test. If you have more than 2 samples, you might have to do something like an ANOVA analysis, but for now, don't worry about that. Everything we'll be doing for now that requires stats will require a t-test. And so what we do is we go back to our caption, and I could copy and paste this, 4.29 times 10 to the negative 5th, okay? That'd be fine. Or I could say, with a number this small, that p equals less than 0.05. That would be okay as well. But I'm going to go in here and just say p equals, and I'm going to paste it in there. Okay? That's one way to do it. Or you could say p equals less than sign 0.05. That's the other way to do it. Okay? That's your caption and your t-test. And you would turn this in. This is a figure, right? If I was asking for a figure, you would turn this in. And then you would also include this page from your Excel sheet so that your instructor can see your work, so they can see what you did. All right, so that's how we make a column graph. Now, if you ever have to make a scatter plot, I have videos on that on the lab website, and I'll just point out before I go how to know which kind of graph to make. For all the experiments you do in this course, you will either do a column graph or a scatter plot, which is basically a line graph. And how do you know which to use? Well, if your x-axis has categories, Arkansas, Missouri, male, female, bird, snake, whatever, categories, and then the y-axis is numbers, then you'll use a column graph. If both axes are lots of numbers, and you usually have more data points than 2, like heart rate and minutes of exercise, then you'll use the scatter plot feature in Excel to graph that. Okay? So you can find more info on that on the lab website on how to make those graphs. And that's it for this one.